right? I thought there'd be data. Is anyone out there?
Any questions on the homework? How's that going? Yeah, you're gonna have to compute, you're gonna have to find the PDF for the maximum, and then if you recognize it, you might be able to just read the mean somewhere. Oh, actually, you won't recognize it. The maximum for n uniform 0, 1s has a beta distribution, but this is uniform 0 theta, and it has not exactly a beta distribution, but it should be a pretty simple actual integral, but just a power, like x to a power, to find the mean. Creepy. I think you can find that expected value by just starting to write out the integral, but I also think it's easier, just my opinion, to look at the random variable yi defined to be the log of 1 plus xi. If you first make the transition to that, you're going to see a very familiar distribution that you already know how to sum and you already know means and variances for. You've got the Pareto distribution, and you want to look at a sum as I goes from 1 to n of the log of the 1 plus xi. And that was just to give you a hint on where to start for an unbiased estimator. And later in the course, you'll know how I came up with that. But right now, it's just kind of an exercise. And so, yes, okay, so obviously the expected, if the x's are independent and identically distributed, so are these logs. So this is like a sum as I goes from 1 to n of yi. And the expected value of t is going to be the expected value of that sum. And then you can pull the sum out because they're identically distributed. And you'll just have n times 1 of the expectations. So what I think you were saying was that you were trying to find the expectation. That's a y. Oh, that's actually a y1 or a y5. So you can, I think you can actually do a substitution and get this, the log of 1 plus x. However, I think you're going to need my hint for other parts of this problem. So you would have, I'm not going to follow through with this. So even if you can do that, I still think it's going to be easier to look at, so it's not wrong. I would find the distribution using the G inverse stuff of y1 being the log of 1 plus x1. It has a nice known name distribution. Four should be very easy because it's what we were talking about last time. I would use for number 4 the weak law of large numbers, which says that if x1 through xn are IID from any distribution with mean mu and variance sigma squared, then x bar converges in probability to the mean mu. So in part A, you just want to know what x bar converges in probability to, and you've got a geometric distribution, and you can just grab the mean out of the table and you are done. I mean, it's not even a one-liner, it's just a marginal note. In part B, I don't think we've looked at anything like this, so I do want to talk about this. You're finding well, there's two things. One is I used an indicator in kind of a different way. So in 4B, I wrote this indicator that says xi is greater than 0. And that doesn't look like the normal notation. But what this means is just a faster way to write the integral from 0 to infinity and then plug in xi. And that's a random variable, actually. So this indicator has become a random variable. So this is just a thing that takes on the value 1 when xi is greater than 0 and 0 otherwise. But check this out. It is random because the x is still capital. And we can talk about the expected value of this indicator. So the indicator is a nice, simple, discrete random variable, and it takes on two values, 0 and 1. So it's going to be 0 times the probability the indicator is 0 plus 1 times the probability the indicator is 1. And so the first part disappears, right? And as for this term that remains, the indicator is 1 if and only if that event being indicated happens. So this is the probability that x1 is greater than 0. I did definitely want to go over this because I haven't talked about expected values of indicators. It's a simple 0, 1 kind of thing. And so anytime you're computing the expected value of an indicator, it's a probability. And you can get this for the geometric distribution as 1 minus the probability x1 is 0. So you don't have to sum up everything above 0. And so the sequence y1 through yn is just kind of a Bernoulli sequence. And yeah, so now it should be a simple one-liner to report what y bar converges in probability to. For problem 5, very short. If you use one of the inequalities we talked about, the pre-Markov or Markov or Chebyshev, you can bound the probability that you care about with this expectation and then take the limit and force something to something. And it's also a one-liner. We've never seen anything like 6, which is, it's an exponential with rate 1, but it has been shifted to start at theta. But there's nothing really special about it. You can still find the CDF, and I'm not going to do much of 6 because I don't think you'll have a hard time with it. But the CDF in 6 is going to be the integral from the bottom of the space, which is theta, up to x of e to the minus, say, u minus theta du. And so if you can find that CDF, then you can find the CDF for the minimum. And remember, a consistent estimator is something that converges in probability to the thing you're trying to estimate. Okay, so any other questions on the homework? We certainly can talk about this Monday as well, or emails over the weekend. So we just defined convergence in probability, and we say that xn, and then we put an arrow with a p over it, converges in probability to a random variable x if for any epsilon greater than 0, the limit as n goes to infinity of the probability, so this is a limit of a sequence of numbers. These probabilities are between 0 and 1. xn minus x being greater than epsilon, it shouldn't be greater than epsilon. They should be getting really close together, so this should be going to 0. And we can also write less than or equal to epsilon and have it go to 1. And it doesn't really matter where the equality is. Strictly less than epsilon should go to 1, or greater than or equal to epsilon should go to 0. And we were in the middle of a theorem. I meant to write this up before I came in here to not waste your time with this, so I'm just going to be kind of fast and sloppy. Do we have convergence and probability of a sequence of random variables xn to a constant a, and some yn's converging to a constant b, and this absolutely could be a random variable and a random variable, but we're not really going to need it for our class, so I just wanted to state it a little more simply, or at least for the proofs. And we were in the middle of proving one, which said that xn plus yn converges in probability to a plus b. Now that I think about it, the proof we were doing is going to hold. It's going to just hold for random variables as well. But I'll just continue what we were doing, which we did finish, but it was kind of rushed. And I think there were some concepts in there that were a little tricky if you're not up on your probability. So a times b and xn over yn converges in probability to a over b if b is not 0, and also if the left side makes sense. So if yn is a normal random variable that takes on values from minus infinity to infinity, even though it can take on the value 0, it doesn't matter because that's going to happen with probability 0 for the continuous thing to fall there. But if it's discrete and takes on 0 values, then you do have to be careful with that statement. And then the final one was we had a function g that's continuous, or at least just continuous at a point A. And then we had that g of xn is converging in probability to g of a. So we were proving 1. And so I decided to look at the greater than epsilon version of this just because, you know, I tried working it out and it just was more convenient. So if we look at the probability that the absolute value of xn plus yn minus a plus b is greater than epsilon. And of course, at the beginning of the proof, you should fix an epsilon. So I reorganized this. This is not really doing anything at all, but I wrote this as the probability that xn minus a plus yn minus b, still in absolute value, is greater than epsilon. Okay, so here's where I use the triangle inequality. And so, you know, the triangle inequality, sum a plus b in absolute value is less than or equal to a plus b, each in absolute value. And so if this left side is going to be greater than epsilon, then this side is more likely to be greater than epsilon, which is why I get a larger probability. So I get a less than or equal to if I break it up like this, moving the absolute value onto each part. And then, maybe I didn't have to go through this again, but so I was making an argument that this event, this is the event that you observe your xn and yn such that the absolute value of xn minus a plus the absolute value of yn minus b is greater than epsilon. And this is contained in the event, you know, it's kind of like the event that you roll a 2 on a 6-sided die is contained in the event you roll an even number. So it's contained in the event where we can say that xn minus a is greater than epsilon over 2, or, meaning like a union of these two events, yn minus b is greater than epsilon over 2. Because in order for the sum to be greater than epsilon, we need at least one, if not both, but we need at least one to be greater than epsilon over 2, because you can't add up two numbers less than epsilon over 2 and get something greater than epsilon. So it could be this one or both. And this is strictly a larger containing event for this, because if you have this event occurring, it could mean that only this happened, you know, in the union, right? You get one or the other or both. And if only this happens, and y is so close to a that this distance is very small, that doesn't mean that you necessarily get greater than epsilon. So this event here is like properly contained in this event. And so we get to use what is called monotonicity of probability, which is if you have a set A that's a subset of B, the probability that A occurs is less than or equal to the probability of B occurring. So we get the probability absolute xn minus A is greater than epsilon over 2. Erase that union, it's in my way. Plus the probability yn minus B is greater than epsilon over 2. Okay. And then we're done. And that is where we were, but I was afraid that some of these small points didn't make it through, because we did assume that xn is converging in probability to A. So here I have another epsilon. It happens to be the original epsilon over 2, but I do know that this guy is going to 0 because the xn is getting close to the A, so it won't be, the distance between them won't be greater than epsilon over 2. And I do have that this guy is going to 0. So this is since xn converges in probability to A, and since yn converges in probability to B. So I won't rewrite this whole thing because you've seen this twice now, but I would start with the very first thing I wrote down, and then say it's less than or equal to this very last line, and then take the limit on both sides. And then you can conclude that the limit as n goes to infinity of the original thing, which was absolute xn plus yn minus a plus b greater than epsilon, this is going to something less than or equal to 0, which forces it to be going to 0 because probabilities can't be less than 0. So we are done. I think there's some good things to have been learned in there, whether or not you want to prove this or can prove it, about subsets and, manipulations of probabilities. So we don't want to go through all of these. I want to prove 4 only because I want to do at least one more, and 4 is really quick and useful. So property 4, this is the one that said if xn is converging in probability to A and G is continuous, or at least just continuous at A, that's all we're going to need, then G of xn is converging in probability to G of A. And so you just need to think about what it means for G to be continuous at A. So we've got a horrible line. I've got some function G, and I'm going to look at some point A, right? And you already know, I'm sure, that if you want, if you look at G of A, that you should be able to get to within epsilon of G of A for some kind of delta distance away from A. So what you know, even with non-randomness, is if x minus A is less than delta, that implies that G of x minus G of A is less than epsilon. Again, I forgot to start with an epsilon, so let epsilon be greater than 0 and find such a delta. So these two events over here are not equivalent because look, in the picture I've drawn, there are other ways for G to be within epsilon of G of A. So for different intervals of x, it could also happen that G is within epsilon of G of A. So but all I need is at least, I don't need these to be equivalent. So we're just about done. So I'm going to take any epsilon greater than 0, and the probability that absolute G of xn minus G of A, this one, because of how we think about continuity, it's going to be convenient to write with the less than epsilon. This is greater than or equal to the probability absolute xn minus A is less than delta. And then xn converges to A in probability, so this guy goes to 1, right? You don't have to think about, was it less than 0, 1? Just think about what it's saying. This is getting smaller than this, which is what you want if xn is going to A. It's getting very small. So that goes to 1. And so you can finish this off by saying the limit as n goes to infinity. This is greater than or equal to 1. And then, of course, probabilities can't be greater than 1, so this turns into an equal. You're going to be using this a lot with multiplying a sequence of random variables by a sequence of real numbers, because real numbers are just boring random variables. Actually, before I say that, let me prove to you that this is kind of a silly example of convergence in probability, but suppose that an is a sequence in R, in the real numbers, of real numbers that converges in the real number sense to a number A. So my claim is that they also converge in probability, which is weird, but technically true. Because I'm going to take an epsilon greater than 0, and I'm going to look at the probability that absolute an minus A is less than epsilon or greater. And I want to take the limit as n goes to infinity. And so there's nothing random in this probability statement. So all of these probabilities are either 0 or 1. And because an is converging as a sequence of real numbers to A, it's eventually going to be 1 when n is large enough. It could possibly be that the ANs are always close to A, but this is probably looking like some kind of sequence of probabilities that eventually hits 1 and stays at 1. So this limit is going to be 1. So its convergence and probability of a sequence of real numbers, and how that might be useful to you is, for example, suppose x1 through xn are IID from some distribution with mean mu and variance sigma squared, and suppose that sigma squared is finite, then by the weak law of large numbers, we know that the sample mean converges in probability to the true mean of the distribution. And you'll see that written all the time, but it might look weird to you because you don't see any n's, but there are n's in here. And if it makes you feel better, then you should write your sample mean as an x bar sub n so you can really see the n. So we already knew that. And then now we know this is going to come up in estimation. So we've only done found a couple of estimators so far, but first you kind of guess and then you kind of adjust it. And so it's not going to be uncommon to see something like an x bar times an n minus 1 over n. I just made this up right now. It didn't really come from anywhere, but it comes from the idea of, oh, I took the expected value of x bar and I didn't get what I wanted to see, but I will if I adjust it with constant. And we do know that this still converges in probability to mu because the x bar converges in probability to mu and the sequence of constants converge to 1, which you can say is in probability. So this becomes like 2 in that theorem, xn times yn. So that's where I think you're going to get the most use out of this theorem. And if you had something like, I'm not using this board very well, but if you had like a constant a, you can say that this converges in probability to a mu, and you can either use a sequence of constants that are constant in time as well, or you can use like g of x equals some a times x, or yn equals a for all n, either one of those. Okay, so with that, one more thing I want to remind you of, I think I did when we talked about the homework at the beginning, but if you want to show that something is a consistent estimator of something else, that means you want to show convergence in probability. And now we get to talk about convergence in distribution. This one is relatively super easy. Is that a thing? Definitely relatively easy to show compared to convergence in probability, but it's also a kind of weak thing. It's a weak type of convergence. So convergence in distribution. So first I'm going to define it. So I'm going to let xn be a sequence of random variables with CDF. So the CDFs are going to be potentially changing. I'm going to write f sub n of x to denote the CDF for the nth one of these. And I'm going to let x be a random variable with some CDF that we're just going to call capital F. So we say that the xn converge in distribution to x if the CDFs are converging. It's just a pointwise convergence. And let me write that down and then I'll tell you why that's super weak. So we say that the xn converge in distribution to x if the limit as n goes to infinity of f n x equals f of x. And then there's a technicality I have to throw in here, which is a little more than, like usually there's some technicality that I just want to put in for completeness, but you don't have to worry about it. But this one, you don't have to worry about, but you're going to find helpful, I think. This convergence has to hold at all points of continuity of the f. And I'll give you an example of why you care about this. So before that, the notation, there's several notations being used. I am going to use xn and then an arrow with a lowercase d on it to x to denote convergence and distribution. Very often people will use a capital D, but if I do that, I really risk it looking like a sloppy P, so I'm going to use a lowercase d. People also call this convergence in law. So sometimes you'll see xn with an L over the line, either like an L like that or sometimes like a script L. And a lot of people will use the notation xn and this double arrow x. But because I'm writing that all the time as implies, I don't think you would actually be confused by it, but I decided I don't want to use that because you'll see those arrows everywhere. And as with the indicators, you can choose any one of these, and that's fine. I'll know what you mean. Okay, so a couple of things to note. Okay, 3 things to note. So 1, this is weaker, and we're going to prove this, than convergence in probability. This is weaker than convergence in probability, i.e., if xn converges in probability to x, this implies that xn converges in distribution to x, but not the other way around. And we're going to prove the implication, and we're going to see an example that shows you that the other way around is not necessarily going to hold. The second note is that this is the type of convergence used in the very famous central limit theorem in statistics. Probably a bunch of you have heard of it, but if not, it doesn't matter. We're going to cover it from scratch in here. But just so you know, this is the type of convergence used in the very famous central limit theorem, which says that if you look at a sample mean and then grab another one, another sample mean, another one, another sample mean, we know that that statistic has a distribution. And as n goes to infinity, that distribution for the sample mean is going to become normal, like a bell curve, even if you started with a very differently shaped distribution. So and the third thing I wanted to note is that the reason this is so weak is because it's really weird in terms of convergence. It doesn't say anything about the xn getting close to the x's. So note, oh, I can't put note under my note. This is saying that note, the xn's aren't getting close, really, in any sense, to x. So let me give you an example of this. Suppose that x1, x2, all the way up, xn, these guys are IID with a normal distribution with mean mu and variance sigma squared. Yeah, you read that right. This distribution doesn't depend on n. This would be kind of interesting if we had like a mean n mu, but this is a non-interesting example. And then if we let x also have a normal distribution with mean mu and variance sigma squared, then the CDF for the xn, this is the probability that xn is less than or equal to x. By the way, for the normal distribution, we can't integrate the CDF, and we can't get the CDF in closed form. People in statistics use z-tables, which means that someone has numerically approximated it, but the CDF for the, I was going to talk about the standard normal again. Let me not go there yet. So I can't write this down. However, it's exactly the same as the CDF for x, just by design of this silly example where nothing depends on n, which is the CDF for x. So if you take the limit of the fn's, yes, it goes to f, right? There's no n moving. So this is the limit as n goes to infinity of f of x. And this is f of x. So we do have that this silly sequence converges in distribution to x. But if you start kind of sampling from the normal distribution, you've got this bell curve, potentially very wide if sigma squared is large. And x1 might be here, and x2 might be here, x3, x4, x5, x6. They're not getting close in any sense at all. And x might be right here, but they're not approaching x because it's saying something about the whole distribution, not the actual random variables. So it is weird to say that xn is converging in distribution to x. You would think people would say the CDF for xn is converging to the CDF for x. Let's do an example, and then let's maybe we can prove the second note, no, the first note, that convergence in probability always implies convergence in distribution. And sometimes the other way is true. So here are a couple of examples. I'm going to take x1, x2, etc. IID from the Pareto distribution with parameter gamma. And I'm going to say, let's investigate the convergence in distribution of, so that when you see that, that means it's, well, that's pretty clear. It means it's the convergence in distribution problem. So a sequence of random variables yn, where I define yn to be n times the minimum of one of the x's, the minimum of a sample of size n. This is one case where you might want to use the other, I'm just going to keep it consistent, but we talked about another notation for the minimum being 1:n, which would kind of look better here because you don't see the dependence on n. And as long as you know it, we can do it. Okay, so we're going to find the CDF for yn. Like, this is so much easier than the epsilons and the absolute values and the sets contained in other sets. We just have to find fn of y. We're going to define that to be, you know what, sorry, I got ahead of myself. Now I can just make it a side note. We're going to need the CDF for the x's. So the CDF for any of the xi, you don't even need to put an I there, they're all the same, is going to be the integral from the bottom of the space, which for the Pareto is 0, up to x, of the Pareto PDF, which is lambda over 1 plus, I always like to change the variable if I'm integrating up to x, so 1 plus u to the gamma plus 1 du. And if you rewrite this as gamma 1 plus u to the negative gamma minus 1, you can see that it's a simple substitution power rule thing. I'm not going to drag you through it. And you'll get 1 minus 1 over 1 plus x to the gamma. I'm going to need that, so I had to write that down. So back to the problem on the left side, the CDF for, I'm using this fny and I'm defining that to be the CDF for yn. Absolutely, you can write f sub yn of y. That's just a lot of subscripts, so. Okay, so what do we know about yn? We know that it's n times the minimum. I'm going to plug that in. We know how to find probabilities for the minimum, so let me get rid of that n and move it to the other side. The thing that I say that convergence and distribution is easy to show, and that's because it's very mechanical. Write down the CDF and take the limit. You don't have to be clever unless, the CDF could be hard to write down. Okay, so remember that when we want to find the CDF for a minimum, I always draw the line and I say, oh, if we want the minimum of a sample to be less than x, that doesn't tell me where everything is, so we do a 1 minus kind of thing. So this is 1 minus the probability that the minimum is greater than y over n. And because these guys are IID, you can draw the number line, but it means that one of them is greater than y over n, that probability to the nth power. So I'm not going to use the minimum notation anymore. I'm just looking at one of the n's. And this is 1 minus the CDF for x1 evaluated at y over n. And I have that CDF up here. So we get 1 minus another 1 minus. This turns into a 1 over 1 plus x to the gamma oops, sorry, not an x. So I'm going to remove that x, but to the nth power. And instead of x, that x should be y over n. Okay, so let me rewrite this as 1 minus 1 plus y over n to the negative gamma to the nth power. And when you raise something to a power and then to another power, you get to multiply the exponents. That thing in front is a 1. It looks really strange. So now we have to take a limit. And there's really only 2 limits you need in this class, I think. So you need to know how to take the limit of like a sequence of numbers. Like if you have numbers between 0 and 1, then that clearly is going to 0. And the other one is the limit definition of e to the x, which you can write as the limit as n goes to infinity of 1 plus x over n to the n, which is the kind of thing we're seeing here. Okay, so hopefully you've seen those. So let me rewrite this as 1 minus 1 plus y over n to the n, like raised to the minus gamma. And the thing inside here is going as a sequence of real numbers to e to the y. So this whole thing is going to 1 minus e to the y to the negative gamma, which is 1 minus e to the negative gamma y. That is the CDF of the exponential distribution with rate gamma. And we've seen that one a few times, but you don't usually recognize CDFs as much as PDFs, especially because you have the PDFs in a table. So at this point, if you don't recognize the CDF, you would take the derivative and figure out what PDF it matches. But what we have shown here is that, so this goes as n goes to infinity. So we can conclude that the yn, which is n times the minimum in the sample, converges in distribution to a random variable x, where I'm going to write it out this one time. Usually people will just kind of shorthand this and say converges in distribution to an exponential. Heck, you weren't supposed to show up. Okay, where x has an exponential distribution with rate little gamma. So what I was just trying to say down there was like a shorthand for this is just to write the name of the distribution, but that's not exactly right. Well, it's just notation. It's not wrong either. Let's not write that until we get comfortable with this stuff. Let's do it by the book the first few times. My next example was going to show you why that at all points of continuity of f was important. And so we're not going to be able to get through this, but I just wanted to start for the purpose of forward momentum. A second example where I have x1, x2, IID Pareto with parameter gamma, and I want to investigate the convergence in distribution of, so before we looked at yn defined to be n times the minimum of the x's, and now I just want to look at the minimum of the x's. I put that n in there before to make an interesting problem. So I don't have time to finish this, but let's just sort of think about it for a second. The Pareto distribution, it gives you values between, not even that hard, between 0 and infinity. And if you have a sample of size n, you might get one there, with n x's. And if you get another sample of size n, you might be there, and another one, and another one. You know what? I don't even need another one. If you have one sample of size n, and then you increase the sample size to take a sample of size n plus 1, and a sample of size n plus 2, and n plus 3, and n plus 4, you're going to squish your minimum all the way down to 0. So what we're going to see, last thing I can write, we'll see next time that the limit as n goes to infinity of the CDF for the y's is going to go, it's going to be 0 for y less than or equal to 0, and 1 for y greater than 0. And this is the CDF of a constant that takes on all its probability at 0. I don't have time to talk about this, but I did say that CDFs have to be right continuous, and this is not right continuous. It's left continuous. However, it's the same as the CDF if you flip these. like it matches that CDF at all points of continuity. So that's why that continuity statement is important. And maybe that none of that makes sense, but we'll start with that example next time on mathematical statistics.